Hello and welcome to the fifth lecture of Advanced Material Chemistry course, Functional Materials Part 2. So in last lecture, we learned that almost all the practical devices are made using semiconductor materials. For various regions, those regions also we learn. Then in the solar cells, we learned that solar cells are PN junction based devices that converts light into electrical energy. Then photovoltaic technologies can be categorized into three generations. These are first generation, second generation, and third generation. First generation was based on single crystal or polycrystalline materials, and wafers were used for making devices. In second generation solar cells, thin films were used. So a lot of material requirement was reduced. Then in third generation, we had polymer solar cells, bilayer, bulk heterojunction, and nanostructure bulk heterojunction solar cells, dye-sensitized solar cells, solid-state DSSC, perovskite, and quantum dot for photovoltaics. And we learn all of these solar cells in detail. They are working, their issues and materials. In fact, almost everything, how to make those, almost every part was learned in detail in last two lectures. So today we will see thermoelectrics. So first, let us see the fundamentals. So imagine we have a metal bar. This is on the screen. So this is, since it is a metal bar, so there will be a lot of free electrons in that. And all these free electrons, when no potential is applied or they are in thermal equilibrium, in that case, all of them will be uniformly distributed over the entire bars. Now, let us imagine we start heating one end of this bar with some heat source. So what will happen? The temperature of this will start increasing. This you can say this end will start increasing. So these electrons which were there in this part, they will get a certain amount of thermal energy, higher thermal energy than those. And so therefore, these electrons will start moving in this direction. So as the temperature increases, they will, you can say, this part of this side of the electrons will try to shift in this side. So over the period of time, suppose a temperature which was uniform initially on both the ends, now the temperature will be different. So let us consider here it is T1, here it is T2, and T1 is greater than T2. So with this increase in temperature, these electrons will move towards one side. So what will happen, since electrons carries negative charge, so this part, if you see on some absolute scale, this side of the rod will be slightly negative as compared to this side. So if I try to visualize the potential between these 2 points and these 2 points, suppose that is V2 and V1. So it will be more negative. This side will be as compared to this side, it will be positive. So a potential will be developed across this. You can say across this bar. So this temperature gradient, when a temperature gradient is applied across a metal or semiconductor, a temperature gradient, you can say a potential is developed because of movement of these charge carriers. So this potential difference is if we measure. So So at certain stage, built-in potential starts resisting further diffusion of charges. Why? So it is not like that all electrons will move from this side to this side. What happens after some time? This portion, this end is negative, this end is positive. So if more electrons wants to move from this side to this side, these will be repaired by this potential. So as we saw in case of solar cells also, there is a diffusion of electron or carriers from one side to another side, and because of that diffusion, a potential is developed, and then that potential, because it is in opposite direction, it starts opposing the movement of carriers. Similarly, the situation is here. The temperature is increased one side, and because of that temperature, the carriers gains energy and they move from this side to another side. Because the carriers are moving, therefore, a net charge is moving from one side to another side, and therefore a potential is developed, and this potential then opposes the further movement of these carriers in that direction. So at certain after some certain time, an equilibrium will be established. So under this equilibrium, if we measure, so there will be certain potential V2 that can be measured, and there will be a definite temperature gradient. That is, gradient is what is called T1 minus T2 divided by the length of this rod. So now let us imagine this was only one rod. So in this one rod, some potential is developed. It was suppose it was at let us say 0, and it was at V1 potential when the temperature increased to T1, and this is suppose at room temperature. And so if it is same metal, in that case on the other also same potential will be developed if the length is same, everything is same. If I have used two wires of exactly same materials, in that case the potential at this point will be same. So if we measure potential here, potential difference here by some voltmeter, it will give me the 0. So it will not be of any use. It will not be of any use is not correct word, but it will not be useful for like our thermoelectric circuit. So what happens? Suppose I use some dissimilar material. So I have used one material which is suppose A, and I use another material which is of B. These have different properties. So those both are both of these materials are suitable for conduction of the carrier. So if it is insulator, then there will not be any potential development. So these two metals are, these two materials are not exactly same. They have little bit difference in some properties. So if we use two dissimilar materials and join at one end here and heated this you can say, and if we heat it to a higher temperature, here suppose now we will call it pH, it is higher temperature, and keep both the other ends at suppose room temperature, that is called TC, or at some lower temperature at the same temperature. Then this potential difference, whatever potential difference is developed, delta V, that is measured, and then this potential, this temperature difference. So this temperature difference, we can see now the temperature difference can be converted into potential difference, and this effect is called as the Seebeck effect. If we divide this potential difference to the temperature difference, then it is called as the Seebeck coefficient. So we can define Seebeck coefficient as delta V by delta T. In some books it is the S, in some books it is alpha. So earlier in older text it was X. Seebeck coefficient was defined as S. Normally, nowadays we use alpha, so we will use alpha in the further discussion. So, the- if we need to define Seebeck coefficient, we can say that it is actually potential difference generated per unit value of the temperature difference. So we have a one hot end, we have one cold end, and there is a temperature difference of delta T. So a potential difference is generated delta V Sorry for the interruption. There was some internet issue. Uh, so I was telling that in place of these two materials, suppose I use one P-type material and one N-type material. I replace them. So we know that in P-type material, the carriers are holes. In N-type materials, the carriers are electrons. So in the same temperature difference, both will move in the opposite direction. So, so that can be utilized in making the thermoelectric devices. We will see. So then the performance of this thermoelectric device depends on a figure of merit. Now we define an important parameter, that is figure of merit, which is alpha square sigma divided by K and multiplied by T, and this is called as the ZT. ZT is defined for any thermoelectric material, and where alpha is Seebeck coefficient, sigma is electrical conductivity, K is thermal conductivity, which includes two parts, electronic part and lattice part. I will explain later also. And T is the temperature. This multiplication of T in both sides is done to make it dimensional. So ZT is that ZT has no unit, it is a dimensionless quantity. So for commercial applications, normally ZT should be more than 2, and the conventional materials, thermoelectric materials, have ZT of the order of 1. A good thermoelectric generator material should have, so it should have as high as possible ZT value. So for that, it should have high Seebeck coefficient, number 1. It should have high electrical conductivity, and it should have low thermal conductivity. So by this formula, we can see then ZT will be high. And the conversion efficiency of any thermoelectric material is defined using this ZT value is using this formula, that is TH, the hot temperature, minus TC divided by TH, and then square root 1 plus ZT minus 1 and square root 1 plus ZT plus TC by TH. So efficiency, if we have typical efficiency of the thermoelectric materials falls between 5 to 8% only, and if we somehow get efficiency of 10%, that is considered as a very, very good efficiency. So these two are different things, ZT, which is called as the figure of merit, and efficiency. So figure of merit is generally it is in range of 1 to 2. It can be higher also in some cases, but now ranging between these and say 5 to 10%. Then if we try to see a thermoelectric power generator, now we know that what thermoelectric material is, how it works. So suppose you have a hot end and you have a cold end, and between this hot end and cold end you put a TEG device. So I will go one by one. The working of thermoelectric generator is based on the Seebeck effect. Thermoelectric power generator is a solid state device that converts heat directly into electricity. So this is my TEG. So it is one side, it is you can say at temperature which is higher, another side temperature is cooled. So there is a temperature difference, and this temperature difference is converted to the electricity. That is a thermoelectric power generator, and this is a solid state device. It consists of a heat source which is kept at high temperature and a heat sink which is maintained at the temperature less than the heat. Sorry for the interruption. Again, there was some internet issue, so we have lost some time. We'll try to move quickly and try to finish the lecture as early as possible. So the temperature difference between heat source and heat sink causes direct current to flow through the load. So one thing is that here also we have direct current as we were having in the solar cell. In solar cells also we were generating DC. Here also we are generating DC. Maybe comes here. Keyboard. So now there are two things. One is why we should have good electrical conductivity and poor thermal conductivity. Normally, the electrical conductivity and thermal conductivity are related. More the electrical conductivity, the material will have more thermal conductivity. They are goes like as one increases, the other also increases. But now suppose you have a thermoelectric material and it is having a very good thermal electrical conductivity and it is having good thermal conductivity also. So what will happen after some time? The heat will flow because it is having good conductivity. So good thermal conductivity, heat will flow from this side to this side, and this will try to bring both the ends at the same temperature. So temperature difference will cease to act like this. And therefore, you require as low as possible the thermal conductivity so that the temperature gradient across this PEG is maintained. However, at the same time, you need the higher electrical conductivity so that carriers can move freely. So you have to optimize for any thermoelectric power generator two things. One is that to maintain electrical conductivity as high as possible and all these like engineering for thermoelectric materials are only for optimizing these two values. And how do we do this? That we will see because they are normally related. So this is an animation just to show you a typical working of type of it's not a PN junction, but you have one N, one P-type material. Both are joined at one and at the heat source and at heat sink on the other end. And so suppose you have electron and hole, those flows like that, and the current flows through this external circuit. Same thing here. So it is the power generated due to seebeck effect is a single phase DC, and the total power is given by how much? I square R. That is the standard power formula, and where R is this load. So this is the load which is coming. The output voltage and output power are increased either by increasing the temperature difference between the hot and cold ends or by connecting several thermal power generators in series. So how you can increase the power? You can increase the power if you increase the temperature. Accordingly, delta T is increased. If you increase the temperature of hot end and maintaining the temperature of cold end same, or reducing the temperature of cold end and maintaining hot end at the same temperature, or changing. So basically temperature difference is changed, so power is changed. And another thing is that you can add several such units in series so that you can increase the power. The voltage of this generator is given by V equal to alpha into delta T. It is from the same formula, alpha equal to delta V by delta T, where alpha is the seebeck coefficient and delta T is the temperature difference. So this is further like voltage generated by a thermoelectric power generator. All thermoelectric power generators have the same basic configuration as shown in the above figure. So you will be having one P-type of semiconductor and N-type of semiconductor. They are joined together and one side is coupled to the hot end and another side is coupled to the cold end, and between these two the you can say outer electrical connection is made at this end. And then of course, for making this connection, again you have to keep in mind that it is a semiconductor, so you need to make ohmic contact so that there is no question of any rectifying effect. So in a T cascaded devices means when you have added several devices, so you can add these kind of devices in series electrically, and because the upper side is always at higher temperature and lower side is at lower temperature at the lower temperature, and the temperature difference is same, so that is in the parallel. So you have like hot end, you have cold end, so you have many devices, like you have put it like this, many devices. However, these have been connected in series. The electrical connection is in the series. And these you can say these 1, 2, 3 all devices are in the parallel. So this is your typical module which is commercially available in the market, and in this you also see this is one end which you can keep at one temperature. This is the another end which is kept at a different temperature, which is which can be cold, which can be hot also. So and then there are many you can say small units. These are the individual thermoelectric generators. So the entire TE device module, this is complete module. When operated between a hot and cold end, it can convert the electrical heat energy into electricity. In this way, TE couple module can be used as a power generator. So these are like here you can see these are thermally in parallel, and electrically if you use like some more devices, you will connect it like this and then take connection from this point. So this Seebeck coefficient, which was delta V by delta T, it can be on the basis of like other calculations, it can be derived that the value of alpha is 8 pi square m star kb square t T H square and pi by 3n to the power 2 by 3. And this is where m star is the effective mass, as we learn in the first lecture. Kb is Boltzmann constant, T is the absolute temperature, E is charge, and H is the Planck's constant, and N is the carrier concentration. So now there are two important parameters. We learned that one is electrical conductivity and another is thermal conductivity. And this we know from the basics of our physics or chemistry, that both electrical conductivity and thermal conductivities are related. So first let us see how do we define this. So electrical conductivity or electrical resistivity, these are related to carrier concentration through carrier mobility mu, and the formula is like this. So it is electrical conductivity, is resistivity, and it is N E or N Q mu. And thermal conductivity is the property of a material which indicates its ability to conduct heat. So thermal energy can be transported by any type of excitations in a solid. In our case, we are mainly interested in two type of contributions. What are two type of contributions? That is electrons and holes transporting heat. How? When you raise the temperature, what happens? There are free electrons or holes in our material, and they gain energy and they move from one side to another side, and therefore they are carrying the energy from one side to another side, and increasing the temperature for the other side also. So this contribution is called as the electronic contribution to thermal conductivity, represented by Ke. And there is another contribution which is the due to phonons traveling to the lattice. What are phonons? That is the lattice vibration. So now we have two contributions, Ke and Kl, and the total thermal conductivity will be Ke plus Kl. So now the lattice thermal conductivity. Lattice thermal conductivity can be given, this is Kl, can be given by 1 by 3 CLV, where C is the specific heat at constant volume, L is the mean free path of phonon, and V is the average velocity, which is RMS velocity of the phonon. L is the mean free path and it determined by the phonon scattering and phonon impurity scattering factor. The another part is electronic thermal conductivity. As I explained, it is because of the movement of the carriers. So electronic thermal conductivity, it can be given by L sigma T, and can be also given by Ne mu L T, where L is the Lorentz vector with value of this for free electrons. It is having slightly different value for holes. The Lorentz vector changes for electrons in single parabolic band and multi-parabolic bands, and has to be determined carefully for different materials. So this Lorentz vector is different for different materials. At higher temperature, due to excitation of electrons, the electronic part becomes large, and Ke can be expected from K total to determine K. So actually there is no direct way to determine the lattice thermal conductivity. So what we do normally, the total thermal conductivity is measured. How it is measured, that we know by our like there is a formula Q is equal to K dt by dx. So you have a material by this formula where K is the total thermal conductivity. So this K can be find out how much heat actually has been transferred over the gradient dt over dx in the equilibrium state. So by this you can find out the total thermal conductivity, and from that total thermal conductivity, the electronic contribution which has been calculated here, it can be you can say deducted, and then you can find out the lattice contribution. So KL you can find out by this way. Now selection for a good thermoelectric material. So what all these things depends is like electrical conductivity or thermal conductivity. These depends on the one is the carrier density. So how many carriers are there in that material, that plays a very important role for determining the property. So the optimum carrier carrier density is approximately 10 to the power 19 per centimeter cube, and this is for the like heavily doped semiconductors. It maximizes the power factor alpha square sigma. This, and there is one rule to determine the band gap. That rule is called as 10 KT rule. And what is that rule? Suppose operating temperature is suppose my operating temperature is T. In that case, the band gap of the optimum band gap or the best band gap for the material, best band gap for the a suitable thermoelectric material is 10 kT. So the band gap should be equivalent to 10 kT, where T is the operating temperature, and reasoning behind this is that small gaps are generally good for thermoelectric performance, as they lead to higher carrier mobility. However, If the band gap is too small, then thermal excitations of the minority carriers will adversely affect, because electrons and holes carry heat in opposite direction. So if the band gap is very small, in that case, at any temperature, because of that thermal excitation, the electrons or holes will move from one band to another, and it will be a problem. Then another thing is that electronegativity difference is a measure of the covalence of the bonding in the material. Large electronegativity difference indicates ionic bonding, large charge transfer, and strong scattering of electrons by optical photons. These large scattering causes low carrier mobility. Therefore, good thermoelectric materials are composed of elements having small electronegativity difference. Now, the good thermoelectric materials will have a large average mass, as heavy atoms correspond to low thermal conductivity due to small acoustic photon generated. And mass fluctuation scattering can be used to reduce the lattice thermal conductivity. Then crystal structure with many atoms tends to have low lattice thermal conductivity. One argument is that the number of defects per unit cell tends to grow as the size of the cell increases. If you go on increasing the size, the defects will continue to increase. So crystal structure that have highly coordinated ions tends to have lower thermal conductivity, though it is an empirical relation only. So if we try to say plot in this figure, so what it is showing, so this is on this you can say axis, we have put the carrier concentration starting from 10 to the power 17, 10 to the power 18, 19, 20, 21, and more this side. If you see, for as you increase the carrier concentration, the alpha value of alpha, it falls like this. And the conductivity, the electrical conductivity, as you are increasing the number of carriers, the conductivity increases linearly like this. This is the, it is directly proportional to the number of carriers. So alpha and sigma, which are at the numerator part, are following. If you increase the carrier concentration, they are following these two plots. If you multiply this curve with this curve, what you will get is this curve. So now I have got my sigma alpha square. The plot is like this. Now, if you try to see the thermal conductivity part, this was the electrical conductivity. So thermal conductivity, lattice thermal conductivity is constant, and electrical conductivity, the electrical thermal conductivity, as the electrical part of the thermal conductivity is, we know it is also directly proportional to the carrier concentration. So as carrier concentration increases, it will also move linearly. So now the total thermal conductivity will be this plus this. So the plot will be like this one, red one. So now if we try to figure out the ZT value, which is, what is that? Alpha square sigma divided by K and multiplied by T. So it will be like this curve, you divide by this curve, and then divided by the absolute temperature. So the curve will come like, multiplied by absolute temperature. So curve will be like this. So you will have a curve like this. So with this, you can see that at a carrier concentration of nearly 10 to the power 19, you get a max value of ZT, which I was telling in like previous line. three slides before. So for a good, you can say, for like having a very good ZT value, the carrier concentration should be in the range of near around 10 to the power 19. And this 10 to the power 19, which is how much? Normally, the what is my typical you can say atom size or typical molecules in per cc is 10 to the power 23, and my carrier concentration is now 10 to the power 19. So doping is nearly of the 100 ppm level. As this 10 to the power 19 is optimized concentration, and it is best suited for the good thermoelectric material. So now if we try to plot or try to see a plot of having on temperature difference versus the device efficiencies for different ZT values. So if my ZT value is 1, in that case, and temperature difference is across two ends is 500 degree centigrade, then I will get nearly 10% efficiency. And if somehow I get a very good material which is having ZT of 10, in that case, I maintain two ends at a temperature difference of 500 degree centigrade. In that case, how much efficiency I can achieve is about 34%, which is here. But ZT value of 10 is very, very difficult, almost impossible kind of thing. So typical materials are having ZT value between 1 and 2, as I already said. So suppose I consider, and they operate with at a temperature difference of nearly 250 degrees centigrade or Kelvin, both are same when it is different. So then you can have a typical efficiency of nearly 8%. These are for different P-type and N-type material. So with the temperature difference. So suppose I have a material like bismuth telluride. The ZT value of bismuth telluride it varies as a temperature difference like this curve. So for like if temperature difference is nearly 100, in that case I can say the ZT value is 0.8. And if I have a temperature difference of nearly 300, then ZT value will be around 0.1. So this material, by this figure, you can understand that if I want to use this material in a thermoelectric device, in this case, the temperature difference will be nearly 100 degree centigrade between two ends. And suppose my temperature difference is around 400. In that case, I have this material which is PAGS text, and this is compound of silver, antimony, tellurium with this fraction, and then germanium and tellurium with the 0.85 fraction, and then they are mixed together. So you can see for this material, the ZT value is nearly 1.2 at 400 degrees difference or 400 Kelvin difference. So suppose my I have a source which is at 400 degree centigrade, and another end is at the room temperature. Then I can use tags as P-type material. Similarly, it is for N-type material. Suppose you want to see at 400 degrees cent, that PBTE is a good choice. Similarly, at lower temperature difference, around 100, you can select bismuth telluride. So these are different materials, and depending upon the temperature difference between the source from where the heat is coming out, And the other can be you can keep at the room temperature or near room temperature. In like higher temperature ranges, like somewhere in reactors where the temperature is even high, in that case, the silicon germanium is used, where the at around 900 degrees centigrade, you have ZT value for P-type around zero point 0.5, and here in the same for silicon germanium alloy, it is around 0.8. So for like if we conclude here, if you want to use up to 200 degrees centigrade, then bismuth telluride is a good choice, and up to 500 degrees centigrade temperature difference, lead telluride and tags 85. 85 comes from this fraction. This is 85 and this is 15. So, and then if for the temperature difference is even higher, one can use silicon germanium alloys. So now how to reduce the thermal conductivity? In the denominator part. So we require low thermal conductivity to have a good thermoelectric material. So but we know that a material which is having a high thermal conductivity and sorry, a low thermal conductivity and high electrical conductivity is rare in nature. So for example, metals, they have conductivity and therefore have a very low alpha value, that is C, and have a very high thermal conductivity. On the other hand, the glasses have a very low thermal conductivity, but at the same time, the glasses doesn't conduct also electrically. So the electrical conductivity is also low. So a concept was proposed where the material shows low K in glass, just as in glass, but high sigma in the well-ordered crystals. And this kind of the material is called as the PGC or phonon glass electron crystal. To control these properties at will, like whenever we want, it is difficult as they are interdependent. The electrical conductivity and thermal conductivity are dependent on each other. So some there are some ways which people have done experiments and reported. So synthesis of new materials in solid solution. So what is solid solution? Solid solution is solution of two different solids, which has very complex crystal structure and thus very low thermal conductivity. Because of this, the complex crystal structure, thermal conductivity in these materials is low. And another is using materials in nanostructures form, which enhance, which actually, if you use materials in nanostructure form, so it actually reduces the electrical thermal conductivity, and therefore it will enhance the ZT value. The idea is lower structure, like what are lower structure? 0D, 1D, or 2D materials. 0D materials is like quantum dots. Shows higher electrical properties. These are not, they are actually beyond the bulk, as they are reported in the bulk. So to improve the ZT values, the following strategies are you can say used. Like initially in the first generation materials, the point defects were increased inside the matrix, and because of the increase of these point defects, the value of thermal conductivity was reduced. And therefore, as the thermal conductivity is reduced, so because it is in denominator, so ZT will increase, and then you optimize at the same time the carrier concentration and try to increase the electrical conductivity and alpha. So alpha square sigma they increases and the thermal conductivity decreases. Overall, if you will sum, you will find that your ZT value has actually increased. There was another thing which was nanos material to very fine compress and then do hot pressing to make it further condensed. So by this process also you can reduce the thermal conductivity. So this is these are like first generation materials where ZT was nearly 1, and for like second generation materials where ZT is 1.3 to 1.7, both these point defect scattering and optimization of carrier concentration and nanostructures, these things both were used together. And like in third generation materials where ZT is even higher, nearly 2, in that case and then introduction of mesoscale structuring that reduces thermal conductivity, and then doping. So doping induced electronic structure modifications. The doping also creates extra energy levels, and that also is responsible for increasing the electrical conductivity. And then matrix precipitate band alignment for optimization of both K, and it remains unaffected. This alpha square sigma, it remains unaffected. So like some examples examples of introducing point defects. So these are like in bismuth telluride, which has this lattice thermal conductivity of 2.4 watt per meter K, and ZT value was 0.6. Similarly, in this bismuth, tellurium, and selenium compounds, increase of lattice period, it is the large unit cell parameters which provide short mean free path length. And by using boundary scattering, material grind, then make pellets using hot pressing, as I wrote here, and by nanostructuring. So in by using all these, we can improve the ZT value. Then to summarize, the most commonly used material for this generator is lead telluride. Lead telluride is a compound made of lead and tellurium having small amount of bismuth or sodium. Then other compounds used for making thermoelectric power generators are, that is tellurium, antimony, germanium, silver, bismuth telluride, bismuth sulfide, germanium telluride, zinc antimonide, zinc telluride, and indium arsenide. What are the applications of thermoelectric generators? For increasing the fuel efficiency of cars, thermoelectric generators are used. These generators use heat produced when the vehicle is running. So you put a thermoelectric generator connected to the hot part like the engine, where it is producing a lot of heat, and other part you can leave in atmosphere. So this temperature difference will give you an electrical power output. So one can use that heat which is otherwise going waste. Then seabed power generation is used to power supply to spacecraft in deep space missions. In deep space missions, like if you are having a spacecraft which is going much beyond the sun, then you cannot use the solar cells because uh, there is no solar radiation. It is in a deep space beyond our solar system. So you cannot use solar cells. So in those kind of missions, you have no other choice but to use thermoelectric power generators only, even if the efficiency of these generators is low. And therefore, like cold is not a problem because outside atmosphere everywhere is having nearly zero temperature. The hot source can be generated by putting radioactive sources, which are disintegrating and giving you heat in deep space missions. Okay. So these generators are used to supply powers to remote stations, like in solar cells also, where we cannot lay the power lines. This kind of generator can be used. Thermoelectric generators can be used. So then some advantages and limitations of thermoelectric generators. Advantages are as an alternative source of energy for special applications such as deep space missions, remote, inaccessible locations requiring no maintenance and replacement, and harvesting heat emitted by human body, instruments, automobile industries, uh, global warming, etc. That is, it is doesn't have much impact on global warming. So like human body also, because human body is at nearly 37 degrees centigrade. So if you have a device which is a thermoelectric device which is having low operating temperature, or the temperature difference is near 5-10 degrees centigrade, you place that in your at your body. So one part is at 37, another part is at room temperature, and you can generate some microwatt of the power, and that microwatt power is you can utilize for deriving certain low power, very extremely low power instruments like chips and other small, very low power equipment. So some of limitations of the PE generators is high output resistance is required, like for getting high output voltage and power, several thermoelectric generators are connected in series, which in turn increases the total output resistance. Therefore, for transferring high power efficiency, large resistance are needed. Thermoelectric power generators generate less electric power for the same heat flow. That is, they have low efficiency as compared to other mechanical generators. This is one of the limitations. And low thermal characteristics. The heat dissipation of any device depends upon its thermal conductivity. Any good thermoelectric power generator has low thermal conductivity and hence poor heat dissipation. So these generators are efficient only when small power is required. If you need higher power, in that case, the thermoelectric power generators are not very useful. Thermoelectric generators are costly as compared to other generators. Now let us see another effect which is opposite to the Seebeck effect. This is called as the Peltier effect. So in like Seebeck effect, those two junctions were at two different temperatures and an EMF was generated. Here you join two dissimilar materials and pass a current through that junction. So at one end the heat is absorbed, at another end the heat is evolved. So where heat is absorbed there, it will become cold, and where heat is evolved, the end become hot. So at the end, what you will get, you are passing a current, and as a result, you are having two ends where the temperature is at one end, the temperature is increasing, at another, the temperature is decreasing. So normally, what happens? It is one remains at normal temperature and another you can uh, control. You can put to a device which you want to heat or cool. So if two dissimilar metals are joined together at both ends and current is flown, then at one end heat energy gets rejected and in another heat energy gets absorbed. It is opposite to Seebeck effect. If the charge carriers are going from low Fermi level side to higher side, then required energy will be supplied by the lattice, resulting in cooling in the junction and vice versa. So suppose this is a junction, and it is a low Fermi level material, and this is having high Fermi level, and your carrier is moving from this side to this side, so it requires certain amount of energy, and this energy is taken from the lattice. So if energy is taken from the lattice, what will happen? The lattice will the material will cool. So this is you have two junctions A and B. One material is iron, another is copper, and you start passing current. In that case, you will see that at one end heat is absorbed, at another end heat is evolved. So one end will become hotter as compared to other, or one will become cooled as compared to the other one. So this is called as the Peltier effect. So Peltier coefficient is defined like here. Then another effect is Thomson effect. How much more time? Time 20 minutes. 20 minutes. Do quickly. So next is the Thomson effect. So Thomson effect is see, if there is already a gradient inside. Suppose we saw a rod initially, a metal rod, and in that metal rod we have already gradient is existing, temperature gradient. So one part is at higher temperature, another part is a lower temperature, and then you start passing the current. Then heat will be either absorbed or evolved. It will be absorbed or evolved, it will depend on the Thomson coefficient, if it is positive or negative. So this phenomena, like when you are passing a current through a conductor or semiconductor, and there is a temperature gradient in that, then the evolution or absorption of heat, this phenomena is called as the Thomson effect. So if 2 points in a conductor are at different temperatures, the density of electrons at these points will differ, and as a result, the potential difference is created between these 2 points. So suppose these are at different temperatures, so you will see the density as we saw in the first slide itself. As you raise the temperature, the electrons moves from one side to another side. So because of that, a potential difference is created. If current is passed through then if current is passed R, which is heated here, like in this, suppose you have a copper bar, and this bar has been heated at the center. So the temperature at this point will be higher compared to this, and now I am passing the current from this side to this side. So now with this side from here to here, the electrons will you can say flow opposite from this side to this side. So let us see some positive charge is flowing. So a positive charge is flowing from this side to this side. So initially it will see a temperature. This charge, when it is moving, this will see a temperature gradient here, positive temperature gradient. So it is like this. And this point is at higher temperature. The heat will be absorbed during this side, from this side to this side. Now here the temperature gradient is negative because this is at the lower temperature and this is at the higher temperature. Now the charge is moving in this side only. I'm talking about, suppose let us imagine some positive charge is flowing or hole is flowing. So in that case, heat will be evolved. So from here to here, in during this period, the heat will be absorbed, and from here to here, the heat will be evolved. So it will be absorbed along AC and it will be evolved around CV of the conductor. Thus, heat is transferred due to the current flow in the direction of the current. This is called as the positive Thomson effect. So copper, silver, zinc, and cadmium shows the positive Thomson effect. Thomson effect coefficient is defined as 1 by E dq by dx, and you divide it by dt by dx. That is the gradient. So if you want to define the Thomson coefficient, so it is equal to the carrier gradient when if say 1 ampere current is flowing through a temperature gradient of 1 Kelvin per meter. So we saw the three thermoelectric effects, which are Seebeck effect, Peltier effect, and Thomson effect. So the thermoelectric effects, thermoelectric effect is the direct conversion of temperature difference to electric voltage and vice versa. Traditionally, the term thermoelectric effect or thermoelectricity encompasses three separately identified effects: the Seebeck effect, the Peltier effect, and the Thomson effect. The Peltier and Seebeck effects are the most basic of these three and are essentially the inverses of one another, for which reason the thermoelectric effect may also be called as Peltier-Seebeck effect, because they are almost same. Now there is one more difference. When you pass current through any resistance, a heat is generated, that is I square R. So that is called as the Joule heating. But that Joule heating is different than the Thomson effect. So Joule heating, the heat that is generated whenever a voltage difference is applied across a resistive material, is somewhat relative, though it is not a thermoelectric effect. You cannot call it a thermoelectric effect. The Peltier, Seebeck, and Thomson effects are reversible, whereas Joule heating is not reversible. If you supply, suppose you have a resistance and you are passing a current to that, a heat will be liberated. The filament will become hot. So it is not like that. If you in normal condition, if you provide heat to that filament, the current will not flow to the circuit. So it is not reversible. However, these three effects like Seebeck, Peltier, and Thomson effects are reversible. So you can do opposite. Like for Seebeck, opposite was the Peltier. A thermoelectric device creates voltage when there is a different temperature on each side, and when voltage is applied to it, it creates temperature difference. This can be used to generate electricity, to measure temperature, to cool objects, or to heat them. This is just a summary of like from the beginning which we have done. So these are like present status of some thermoelectric. The highest ZT value is approximately 3.1 at 783 Kelvin, and this is for polycrystalline P-type tin selenide, and efficiency is nearly 12%, and this is at temperature difference of 541 Kelvin, and this is in the segmented device. It's one device over there are 2-3 different devices. And for like this is for inorganic materials, and for organic semiconducting materials, the ZT, highest ZT is nearly 0.42 at room temperature, which is at the P.PSS films. It is the same PSS material which is used in solar cells also as a pole transporting material. So it's a kind of wonder material which is useful in our everywhere. In our laboratory also, in our division actually, not in our lab, but in my colleague's lab at BARC, thermoelectric work is going on, where we have developed several thermoelectric materials in different temperature range. One is low temperature range, one is mid temperature range, and higher temperature ranges, or you can say segmented. PBT and PAGS. So N type of PBT is this material, and P type of tags 85. This material is used and where hot end we can say is around at 550 degrees centigrade, and well, this is the picker circuit. So at these devices, they are giving an efficiency of nearly 6%. Similarly, for low temperature range, 100 to 300 degrees centigrade, they are using a material of bismuth, tellurium, and selenium, and bismuth, antimony, and tellurium. That is P-type material, N-type material, and one end is at 300 degrees centigrade, another is at 440 degrees centigrade, and the efficiency obtained is nearly 6.3%. In the segmented devices, where one end is at around 550 centigrade, another is near room temperature, 427 degrees centigrade, then the efficiency is achieved around 12%. So the thermoelectric part is finished. Now we move to the part 3 of this course, which is device working materials, and that is important elemental and compound semiconductors. Most of the things which we have already have an idea about these things in first 2 lectures. So we can quickly go through these materials. And then single crystal growth and techniques, Chaudhary method, Bridgman, cold zone method, hydrothermal growth method, crystal growth of silicon and gallium arsenide production process of vapors, growth of quartz, and thin film deposition techniques, thermal and electron gunner operation, DC and RF sputtering, epitaxial film, deposition techniques, PVD, VPE, LPE, and LB. So all these parts we will see together. Only this part we will be able to cover today in so this part, because we already have some idea, so we will very quickly move through this and so let us go quickly. So now important elemental and compound semiconductors. So we have like this we already have discussed many times. So elemental semiconductors are silicon and germanium. If we see only group 4 semiconductors, then silicon, germanium, and silicon carbide also. So this is both silicon and carbon from 4th group. So from group 4 element, these 3 semiconducting materials are very commonly used. Then if you try to see group 4 and group 6 compounds, then the following semiconductors are used: lead sulfide, lead selenide, lead telluride, and the silicon. There is a silicon property of silicon material, which is very commonly used as a semiconductor. It has a melting point of 1414 degrees centigrade with a boiling point of 3265 degrees centigrade. The density is 2.32 gram per centimeter cube. It crystallizes in FCC structure, which is diamond structure. The thermal conductivity is nearly 149 watt per meter Kelvin. Electrical resistivity is also not very high. If you can see these value, this falls under the semiconducting range only. The band gap is 1.12 electron volt, uh, and thermal expansion is approximately 2.6 micrometer per meter Kelvin. And how it is produced? On the silicon, up to 99% purity is made by reducing sand. Silicon is produced from the earth crust. You have a silica. So a lot of sand is consisting of silica only. So by reducing the sand with highly pure coke, so you have highly pure carbon and then silica. You can say these are together heated at a very high temperature. So this reduction is carried out in an electric arc furnace. Excess SiO2 is used to stop accumulation of silicon carbide. So then you have like SiO2, 2C, silicon is produced, then you have carbon monoxide and the silicon carbide also, and the silica it reacts with the silica, and then also it gives you silicon and then carbon monoxide. We'll come to germanium. Germanium has a melting point which is lower as compared to the silicon. So it is 937 degrees centigrade. The boiling point is 2830. Band gap is low, nearly 0.7 dB. Resistivity is 0.1 ohm meter, and crystal structure is same diamond as with silicon. Density is 5.32 gram per cc. It expands with this rate. With thermal expansion, and these properties are important for the crystal growth purpose. And thermal conductivity is 60 watt per meter thin. And this is 6 micrometer per meter thin. And it is a very widely used semiconductor. It reacts with the oxygen at high temperature and makes germanium oxide. The physical properties, it is a bright, shiny, brittle, like this picture is showing. And chemical properties, it is inactive, does not dissolve with water or react with oxygen at room temperature. It is produced mainly from sapphirite, which is the ore of germanium and contains zinc and sulfur. It also found in the silver, lead, and copper ores. Another source of germanium is fly ash of power plants fueled from coal deposits that contains germanium. Now next comes amorphous silicon. We are doing it specifically because that is the part of syllabus. Separately it is written. So these like all these silicon, germanium, and therefore one by one we are going quickly. And amorphous silicon is the non-crystalline form of silicon used in TFT and LCD and solar cells. In amorphous silicon, not all the atoms are fold coordinated, and no long range order is present. Some atoms have dangling bonds, which represents defects, which leads to anomalous electrical behavior. It is passivative. These dangling bonds and in amorphous also, when they are not coordinated, the passivation is done. So it is passivated by hydrogen, which makes a bond at dangling bond site and reduce their density by several order of magnitude. So you have more saturated bonds there in that case. So such obtained hydrogenated amorphous silicon, called as ASI:H, has a sufficiently low amount of defects, and it can be used to make devices such as solar photovoltaic cell, which we saw, I guess, day before yesterday. It is used as solar cell material with a varying and wider band gap up to 1.9 electron volt. The absorption coefficient of amorphous silicon hydrogenated is very high. It can be deposited by sputtering CVD or plasma enhanced CVD. Can be deposited on variety of substrates such as plastic, metal, etc., and therefore very useful in different type of POS fabrication. Next is 4, 6 compounds, and these are lead sulfide, lead selenide, and lead telluride are important compound in this group. These compounds are characterized by narrow energy gap, high carrier mobilities, and high dielectric constants. They have energy band gap as low as the band gap of this semiconductor is very low, nearly 0.5 eV. The unique feature of the direct energy gap is these compounds is that the energy band gap increases with increasing temperature, which means that energy gap has a positive temperature coefficient that is specific to these materials. Main application of these compounds are in light emitting diode devices, diode lasers, and detectors in the infrared spectral region. Next, in importance to the elemental semiconductor silicon, we have the 3,5 compound semiconductors obtained by combining group 3 elements and group 5 elements. Essentially, 5 elements, what are those? Nitrogen, phosphorus, arsenic, and antimony. And group 3 elements are these 3 are mainly used, that is aluminum, gallium, and indium. So how many different combinations are possible? Using all these 3, it gives us nearly 12 prospective combinations. And the most important ones are probably gallium arsenide. Gallium arsenide is very famous actually. Indium phosphide, gallium phosphide, and gallium nitride. 10 commonly used compounds are listed in the next slide. All these 3-5 combinations crystallize either in the diamond lattice like silicon, or it is actually zinc blende structure, not diamond lattice, because there are 2 components. Or in the hexagonal lattice known as Woods-Wright. Woods-Wright structure is actually we did not study there, but Woods-Wright is like we had. I will just explain in brief, so to completeness. So there are 2 kind of closed spec structures. One is an FCC structure and another is HCP structure. When we were filling those spheres in different layers, we had one layer, then another layer, and then when we were trying to put spheres on the 3rd layer, we had 2 possibilities. We could have put in one groove or another groove, nearby groove. So if it is we put in another groove, it becomes ABC kind of structure, AB kind of structure. Then the structure, which is the closed spec structure only, is called as the hexagonal closed spec. So in place of now FCC structure, if you have a HCP structure, that is hexagonal closed spec structure, and then try to make like those 2 atoms, which were 2 spheres which were of the same size, and you make them of the other size, then this structure is called as the Woods-Wright structure. So you push a sphere between those 2. Those 2, you can say this void in place of the tetrahedral void, now it will become an octahedral void. So you have 3 sphere and then 3 sphere, and between there is a you can say void. This void is now octahedral void, and you try to put a sphere inside that, and then eventually pull both the upper layer and lower layer because of that same size putting same size sphere. So these are the very common and important 3-5 compounds. That is aluminum phosphide, aluminum arsenide, aluminum antimonide, gallium nitride, gallium phosphide, gallium arsenide, gallium antimonide, indium phosphide, and indium arsenide, and indium antimonide. And now we come to second 6 compounds. So these are zinc oxide, zinc sulfide, zinc selenide, zinc telluride, cadmium sulfide, cadmium selenide, cadmium telluride. These are also semiconducting materials. So all these 7 second 6 materials have a wider band gap, and it ranges from 1.5 to 3.6 eV. These have various common applications like LEDs and signal processing. The growth methods vary by materials, but mostly grown by mass growth. Zinc oxide and zinc sulfide, it is not possible to grow by melt method, but other can be grown by melt method, mostly bridgement technique, bridgement crystal growth technique. The crystal growth methods we will see in tomorrow's lecture. So all these can also be grown by epitaxial methods. That also we see what are epitaxial methods in brief. Their advantage is these are less energy loss, so they are more efficient and potential for lower cost. Therefore, because they are more efficient, then they show higher breakdown voltages, higher power and frequency applications. Then because of higher doping concentration, thinner devices applications. And then higher electron mobility leads to the faster operation. So these have higher electron mobility. So these are some of the advantages of these 2,6 compounds. Then there is another component, that is tellurium. Tellurium has a melting point of 449.5 with a boiling point of 988 degrees centigrade. Band gap very small, 0.38 eV. And electrical edge. So at even room temperature, you will see it will pass sufficient amount of current. You will not be able to differentiate whether it is actually a conductor or it is a semiconductor. But if you reduce the temperature, put it at liquid nitrogen, or even bring even lower temperature, then you can see the semiconducting behavior of this material. The electrical resistivity is in this range. The density is 6.24 gram per centimeter cube. The thermal conductivity is 3.38 watt per meter K. Thermal expansion is about it has a higher thermal expansion, about 18 micron per meter per Kelvin, and atomic number that you know. Crystal structure, it crystallizes in a trigonal structure. And the importance is because of its low electronegativity, tellurium form a variety of materials with small band gaps and find applications in photoconductive materials, solar cells, infrared detectors. Then next comes how it is produced. Most of the tellurium is obtained from copper deposits where it occurs in trace amount. Then come ternary and quaternary compounds. So like in addition to the earlier compounds, we have some important ternary and quaternary compounds which are very important for device application point of view. These are also semiconducting. You can call these in semiconducting classes. So far almost all semiconducting materials we have covered in in whatever device they are used. We have covered almost all the materials. So now we have like aluminum, indium arsenide, gallium arsenic phosphide, gallium indium nitride, gallium indium arsenide, gallium indium phosphide, aluminum gallium arsenic antimonide, gallium indium arsenic phosphide, and aluminum indium arsenide. So these are the quaternary compounds, quaternary compounds used in the semiconductor. So with this, we come to the end of today's lecture. I'm sorry, there were a lot of internet connectivity issues, and we had to run to complete. So if you have any question, you can ask me. I'm ready to answer. So there is a lecture tomorrow also. And tomorrow we will see crystal growth method and thin film deposition methods. Well, if there is no question, then thank you so much. See you tomorrow. Bye.